Hey folks, I've got a few examples of Newton's second law involving friction. And what you may want to do is copy all this down. Let me describe it real quick. You've got a block with a mass m. You're pushing on it with a force F at an angle theta to the horizontal. And there's going to be a coefficient of kinetic friction, mu sub k, between the block and the ground. And what I've done here, we had a problem just like this a bit ago without friction, and I drew the FBD. This one is the first, the middle one here is the College Board FBD. Like these are the actual forces that they lie, and then the right hand FBD is the component FBD where we split things into parallel and perpendicular to the motion. So if you need a moment, go ahead and copy that down, and then we're gonna throw in friction here and talk about it. All right, so this is a problem we've already done, except for now we're adding friction. The two things we're going to determine are what's the normal force acting on the crate, and also what's the acceleration of the crate in terms of the givens and fundamental constants, okay? And we have to add friction in here, okay? Now, the box is going to slide to the right, and so the relative motion of the box surface with the ground is to the right. Friction will oppose that motion and will point left. So we have to add friction into our FBDs, and it points left, so I don't have to break it down to components or anything, okay? All right, so that's the one change from that previous problem is we've added friction in here, okay? Now, as far as the normal force goes, it's exactly the same as it was before. You have F normal acting up. You have two forces acting down. They have to balance because there's no acceleration vertically. So I know that F normal has to equal F sine theta plus Fg. Now, we'll go one more step. You weren't actually given Fg. You were given m and the fundamental constant of g. So what you really should write here is Fn equals F sine theta plus mg. Okay, so that would be the normal force. Okay, now as for the acceleration of the block, assuming to the right is positive, okay, then we would write, if I'm using Newton's second law, net force equals ma, and this is now parallel to the motion, so I can put little parallel signs there. Then you would have F cosine theta minus force of friction equals ma. Okay. Now, the change here is we have a minus force of friction. We didn't have that in the previous problem without friction. Okay. Now, I'm not done yet. I need to get acceleration in terms of the givens and fundamental constants. Well, I wasn't given the force of friction. I was given the coefficient of friction. So I'm going to make some substitutions here. So we have F cosine theta minus what's the definition or what's the equation for kinetic friction? It's mu sub k times Fn, and that equals ma. Oops, sorry about that. Put that in there. So m times a. And I'm getting closer, but I wasn't given Fn as part of my problem. But I do know what Fn equals in terms of the givens and fundamental constants. There it is. So I'm going to make that substitution, and we're going to do a little bit of algebra. So Fn is equal to F sine theta plus mg, and this all equals ma, okay? I will go ahead and distribute the mu sub k in here. So we got F cosine theta minus mu sub k times F sine theta, and then a minus mu sub k mg, and that would equal ma. And if I want to solve for a, I would divide all this by m. Okay, and that's going to give me my acceleration in terms of the givens and fundamental constants. And now if I gave you a value for f and mu and theta and m, and you'd be able to plug and chug and get an acceleration out of this, okay? Now, in that previous example we did without friction, okay, I asked you some questions about what if we took the force and stuck it here instead. Same angle with the horizontal, but now you're pulling instead of pushing. Okay, how would all these answers change? All right. Well, first of all, in this FBD, the force would now be directed upward. In this FBD, well, now your F sine theta will be pointing upward, okay? For your F normal equation here, now you would have F normal plus F sine theta would equal mg. So F normal would be mg minus F sine theta. So instead of a plus F sine theta, now you have a minus F sine theta. Okay. In other words, you've reduced the normal force because now you're partially holding this thing up, so the ground doesn't got to push as hard upward to hold the crate up. Okay. And then how would that change your acceleration? Okay. Well, this line wouldn't change, and this line wouldn't change. Here comes a change. You'd have a negative right there, and therefore this would become a positive. Okay. So what would happen to your acceleration? Well, it'd be greater because now you this term here is now positive instead of negative, which physically makes sense. When you go to move, let's say, a heavy object across the floor, do you push down on it to move it, or do you pull up on it to move it? Well, you pull up on it to move it. The reason you pull up on it is twofold. One, you pull up on it to reduce the normal force acting on the crate. Then the second thing is, by reducing the normal force acting on the crate, you are now reducing the amount of friction acting on the crate. And therefore, there's going to be a greater acceleration. Okay. All right, so that's example one. The next example I have for you involves the following. And this involves drawing FBDs very darn carefully. Okay. Let's say we have the ground and you have a book that you've tied a spring scale to that you're going to pull with some force F, okay? And between the ground and the book, there is a coefficient of kinetic friction, I'll call that 1, and a static friction coefficient, mu S1. So I got a mu K1 and a mu S1, okay? On top of the book, you have put let's say a stapler, all right? Between the stapler and the book, there is a mu K2 and a mu S2. Okay, so there's coefficients of kinetic and static friction between the stapler and the book. All right. Now, by the way, I'll call the stapler M1. I'll call the book M2. All right. All right. So I got a really simple question for you. Not simple to answer, but it's a simple question. What's the biggest F can be such that the stapler does not accelerate or does not slide on top of the book? So how hard can I pull the book so the stapler doesn't slide? Because if you pull too hard, you're going to kind of pull the book out from underneath the stapler, and the stapler is going to slide and fall off the book. So what's the hardest I can pull and that stapler not slide relative to the book? Okay. All right. So we're going to draw a couple FBDs. I'll start with the stapler. So that's M1. Okay. What forces act on the stapler? So we've got M1G, that's gravity. I'll call this FN1, okay? And what force accelerates the stapler to the right? Well, it's got to be friction. Now, again, the reason that is the book is trying to move right underneath the stapler. So in the stapler's point of view, the stapler is actually trying to move left relative to the book. Friction will oppose that relative motion and pull the stapler to the right. Friction is the only force we have available to pull the stapler. There's no other horizontal force available. Now, the other question is, what kind of friction is it? Is it static or kinetic? Well, we don't want the stapler to slide, so this is static, okay? Now, if you'll recall, we said force of friction static is less than or equal to mu static times F normal, okay? Since I'm asking you for the maximum pulling force that we can pull with, we're going to use the equal part of this. We want to know the biggest amount, okay? So the biggest force of friction necessary, or the biggest force of friction we can have, okay? Now, this is our FBD. This is actually pretty easy. In the vertical direction, I know that FN1 has to equal M1G, okay? And in the horizontal direction, I know the force of friction static has to equal M1A, okay? And force of friction static is mu static times Fn1, okay? So that equals M1A. Now, again, It's equal to here, again, we've talked about that. It's not less than it's equal to because I'm asking for a maximum force. And then we got mu sub s, and this is m1g equals m1a. And the m1's cancel out, and you have the max acceleration of your stapler is mu sub s1 times g. Okay, so we've got the max acceleration of your stapler. Now, we haven't answered the question yet, but this is a pretty valuable piece of information. Now we have to draw the book, and this gets a little more complicated. So this is our M2. So what forces act on the book? Well, I'm pulling with a force F. I'm trying to determine that in terms of the Gibbons fundamental constants. All right, we got the weight of the book, so that would be M2 times G. Okay. Now, there's going to be friction between the book and the tabletop or the floor, whatever you're dragging it on. Now, since I'm dragging the book across the floor, is that static or kinetic friction? Well, that's going to be kinetic. So this would be force of friction to kinetic. All right. Now, we're, I think, about halfway done with our FBD. What other forces act on this book? Okay. Well, you have the top stapler. The stapler is pushing down on the book. And it would be tempting to say that's M1G. And in this case, it wouldn't be completely wrong to put that down, but technically that's not right. Technically, it's FN1. So I'm going to draw that in. Now, it turns out in this problem, FN1 is going to equal M1G. However, if I gave you a problem where there was some up or downward acceleration, well, then FN1 wouldn't equal M1G, and then you'd be wrong. This is always going to be correct, okay? By the way, this is an action-reaction pair. The book is pushing up on the stapler, and the stapler is pushing down with FN1 on the book, okay? All right, let's see. What else is in contact with the book? Well, the ground, right? So that's going to be, and I'll call that FN2. So that's the floor holding the book up, okay? And I said we were halfway done. We were at 3 forces. There is a sixth and final force acting on this book, okay? And that is the friction from the stapler, okay? So the book tugs the stapler to the right with a force of static friction. The stapler tugs the book backward with that same force of friction static, okay? So book tugs stapler right, stapler tugs book left, all right? So there is our FBD, okay? Now, I'm going to start with the vertical here. I'm going to need to know the normal force FN2. So FN2 has to equal FN1 plus M2G. And we also know from the previous work that FN1 equals M1G. So we got M1G plus M2G. Okay. Now, again, because there's no vertical acceleration or anything going on, you probably already knew this was true, but it's good to prove it. And again, if there were any vertical acceleration, that wouldn't be true. All right. Now, in the horizontal direction, we're going to assume right is positive, okay, in which case you have F minus force of friction static 1 from the stapler minus force of friction kinetic 2 from the ground is going to equal M2A. And now I'm going to do a boatload of substitutions here. So we got F minus force of friction static 1. I already found that, okay. That equals mu S M1G. So I'm going to put mu S, or mu S1, I should say, M1G. So that's force of friction static 1. Minus force of friction kinetic 2. So that's mu K2 times the normal force I just found, which is M1G plus M2G. And this all equals M2, and I'm running out of room, A. And I already found what A has to be. A has to be mu S1G, okay? And basically, I'm just trying to get F by itself, so I will do that now. I'll start with this last term first. So we got M2 times mu S1, oh, I'm sorry. Oh, yeah, mu S1G. Okay, so that was this term here. Then I'm going to do this term. So plus mu S1 M1G. And then I'm going to distribute this mu sub k2 into here. Well, actually, I take that back. I'm not going to do that. I'm going to factor out the g. So minus mu k2g times m1 plus m2. Okay, and I would probably do one more step. Force equals, in these first two terms, you can factor out the g and the mu s1. So it's going to look something like this. Mu s1 g times m1 plus m2 minus mu k2 g times m1 plus m2. And oh, if you're really into algebra, oh boy. So now you could say mu s1 g minus mu k2 g, all right, times m1 plus m2. Okay, so you can factor out the m1 plus m2. Okay, so there's, and any of these, they're all algebraically equivalent. So that's an example of figuring out like what's the maximum force you can pull with so that the stapler doesn't slide with respect to the book. Okay. Now these two examples I picked, they're not exactly easy, especially the second one. The hints on this is make sure you draw your FBD really, really careful. Think really hard about what forces are acting on each object. If you get the FBDs drawn correct, it's a lot easier to actually then do the problem. Okay, so I wanted to pick some harder friction problems because in the previous year's course, you probably did a lot of relatively easier examples with this. So I wanted to pick a couple hard ones for you. So I hope those were helpful, and have a good one.